Okay, we're going to start our orbital motion lecture with the idea uh, that things that are orbiting other objects are really reacting to. Uh, the idea is that they are going at a sufficient speed so that the curvature of their motion is equal to the curvature of the or the rate of change, the curvature of the motion is equal to the curvature of the thing that they're rotating around. And so when Isaac Newton theorized about firing a cannonball fast enough so that instead of just going a long way and traveling along the curvature of the Earth for a little bit, he found that if he launched it far enough, it would curl, or if you launched it fast enough, it would curl all the way around the Earth and return to where it was fired, because the rate of falling of the cannonball would equal the curvature of the Earth, and that was how he originally theorized an orbit. Well, if you extend that out to very large distances and very large speeds, then you start getting objects like moons and planets traveling around planets and stars. So, the first question we're going to start is, how long does it take the Earth to complete one orbit of the Sun? Okay, well, we know this. We experience it all the time. We're about to come to the official end of one of these orbits, and we call it 1 year. Okay, and 1 year equals, for us, is 365. Actually, 365 and... All right, 365.25. 0.25 days. And we know it's a 0.25 because every 4 years we have our leap day, right? It's called a leap year, and we have that extra day. And it's just because it's not an exact science, that the happenstances of our orbit is that we is that our days in relations to our years, we have this extra quarter of a day that it takes for us to go completely around. So we make up for it every year by throwing that extra day into that fourth year. But from this we have the definition of a period, which is the time for one complete revolution of any object around any other object. That is, in fact, it's that way for a cycle, any kind of cycle. So if we have a second hand traveling around a clock, the time it takes to go all the way around a clock is 1 minute, and so the period of the second hand is 1 minute. Okay, so here I'm going to pose a question to you guys. How fast is the Earth traveling? How fast is the Earth moving? Now, mind you, this is specifically in relationship to the sun, because our entire solar system travels around the center of our galaxy at a ridiculously fast speed. But we don't really detect that, and the things that are really only important to us are how fast we're traveling around the sun. So what do we need to know? How fast is the Earth moving? Well, if we're looking for how fast, then we need to know a distance, right? Our speed, or our velocity, equals our rate divided by our time. And so our distance, I'm sorry, not our rate, our distance is going to be, well, how do we tell that for a circle? Well, it's going to be the circumference. And so the circumference here is going to be 2 pi times the radius of the Earth divided by the period of the Earth. And this is how we determine our velocity, our speed in orbit. That's how fast we are traveling at the orbit we have. Yeah, but we're going to have to convert this down to meters per second, so it's going to get a little tricky here. I will tell you that this radius right here, this distance, is 1.497 times 10 to the 11th meters. That is the average. Now, mind you, we have an elliptical orbit, and so on one side of during one part of the year, we are furthest away. We are at apogee, or aphelion is actually what it's called, which is the furthest point away from the sun. And then we have perihelion, which is our closest approach to the sun. They're about the same amount, but there is, because all orbits are elliptical, there is a bit of a transition, or a bit of a change as we orbit the sun. Our aphelion occurs during our winter, during the northern hemisphere winter, and it occurs during the southern, and our perihelion occurs during we are actually closer to the sun during our winter, and further away from the sun during our summer. So we can find this out. We can find 2 pi r's. That gives us our circumference of the Earth. And that winds up being 9.41. Actually, 9.406 times 10 to the 11th meters. And we're going to divide that by our period, which is our number of days turned into in seconds. And so we're going to take 365.25 days, and we're going to multiply it by 24 hours in a day, and 60 minutes in an hour, and 60 minutes and 60 seconds in a minute, to give us 3.156 times 10 to the 7th seconds. And that winds up being 2.981 times 10 to the 4th meters per second, or 29,810 meters per second, or about 30 kilometers per second around the sun. We're traveling 30 kilometers a second all the way around the sun. That's quite fast. Okay, so this is the current speed of the Earth. Well, that's really, really fast. How do we get an object to go that fast? How does an object that's going that fast stay in orbit around the sun? Okay, because this is just its straight line velocity, right? This is just right. So we're just doing that, right? That is how fast we're going at any particular time. Now, mind you, if we're over here, okay, at a different time during the year, then our velocity is going to be in that direction, right? Okay, so that's our velocity vector here. That's our velocity vector here. That means that we are changing our velocity because we're changing our direction. And any time we have a change in velocity, we must have, remember, oh shoot, I want a different color here. Okay, a change in our velocity must be an acceleration. But this speed, this 29,810 meters per second, that doesn't really change. It changes a little bit as we get closer to the sun and as we get further away from the sun. But that is our average speed as we travel around the sun. So there has to be something causing a change in our acceleration, and that is called a centripetal acceleration, that the Earth has is going to be experiencing acceleration at any particular moment in this direction. Okay, so because the only thing keeping the Earth traveling around the sun is the force of gravity acting on the sun, and so the way we measure our centripetal acceleration is this. Oh, that's a big brush. I don't want that. That's what I want. Our centripetal acceleration equals, and that's how we write it, centripetal acceleration. And I'm just going to tell you that it is the velocity squared divided by the radius. Okay. Now I'm going to introduce a new concept. Well, I'll do that here in a sec. This is the centripetal acceleration. So it's our velocity squared our speed squared divided by the radius. Okay. So in this particular case, it's going to be our 29,810, right? So our 2.981 times 10 to the fourth meters per second. And we're going to square that, and then we're going to divide it by our radius, which was the 9.406. No, I'm sorry. That was the circumference, not the radius. The radius was different. So the radius was or 1.497 times 10 to the 11th meters, right? And so that's going to equal, okay, and that is going to equal, and you're going to be surprised at this, 5.934 times 10 to the negative third meters per second squared. That's the centripetal acceleration on the Earth. Right? This is how much it is accelerating towards the center of our orbit. Okay, so this is an important thing to remember. This is centripetal acceleration. All right, this right here, this AC, right, V equals V squared over R. Okay, now there's another kind of velocity we need to talk about while we're here. And that is has to do with our angular acceleration, or our angular velocity. And in order to talk about that appropriately, we need to discuss radians. Okay, and so a radian is, or I'm going to try and draw a circle here. Yeah, that's about as good as I can get it. This program does not do shapes well. A radian is the length of one radius along the circle. Right, so it's one radius of arc length around the edge of a circle. And what happens is, since we have the circumference of a circle, since the circumference of a circle equals 2 pi times the radius, right? If we divide our entire circumference by the radius, so in other words, how many radiuses are there in a circumference, we wind up with 2 pi. That one full circle is 2 pi radiuses, and so we call this angle right here, this angle that is that maps out one radius of arc length along the edge of the circle, this is called one radian. Okay, and so there is some equivalence we have to talk about. If we go all the way around a circle, we know that all the way around the circle is 360 degrees. Okay, and that equals, in this case, 2 pi radians. Okay, now radians, we don't usually write radians. It's just, it has an angle of 2 pi. And so halfway around, right? So if we go halfway around the circle, okay, 1 halfway around the circle is half of 360, so that's 180 degrees. And that equals pi. Pi radians, right? All right, we cut that in half, then that's going to be 90 degrees, and that equals pi over 2 radians. Okay, and you can do the same math. And so essentially, that pi radians. Let me do it the other way. That 180 degrees over pi is proportional to your degrees over your radians. So let's say we take 60 degrees, right? So 180 over pi equals 60 degrees over what number? Well, we know that 180, that 60 is one third of 180, or 180 divided by 60 is 3. And so this would need to be 1/3 pi, right? Or pi over 3. So in other words, the number of radians, because 60 is 1/3 of 180, then our number of radians would be 1/3 of pi. And so 60 degrees equals pi over 3 radians. Okay, so it's that sort of proportion. Okay, so it needs to be bigger. Okay, so those are radians, and we will have more practice at this. We'll have more practice at this as we move on. But this does lend to our idea of angular velocity. Okay, and our angular measurements. And so our angular velocity is given by the Greek letter omega. Okay, this is omega. It is the lowercase omega. Some of you may be more familiar with the capital omega that looks like that. This is reserved, in physics, this is reserved for a unit of resistance, because the unit of resistance is the ohm, and so it would only make sense that the ohm would be symbolized by the letter omega. All right, so let's get rid of that here. Okay, so our omega here, which is a, I'm not doing it justice, so I'm going to drop larger here. It's a, it kind of looks like a butt. It is a script W is a curly script W. Yeah, and so omega equals your velocity. Right, so your meters per second, how fast you're traveling, your speed around the circle, divided by the radius. Well, if we have, all right, so if we're dividing by if our speed divided by our radius, this is going to give us a value in in meters per second divided by meters. But really, this meters per second divided by meters is a radian, right? So this is radians per second. So this is our angular velocities in radians per second. All right, so let's compare here. The period is the time for one complete revolution, right? So this is the time it takes for 2 pi radians, right? Period is the time it takes for 2 pi radians, or 2 pi r over t, right? So, okay, is your angular velocity No, I'm sorry. I'm instructing that wrong. Okay. Sorry, this equals 2 pi, the number of radians, divided by your angular velocity. Okay. Or your velocity times your time equals your distance. And so since you're just traveling in a circle, okay, your velocity times time equals 1 time around one time around the circle. Okay, so let's go over, and so the variables that we've been using are in your book. So the variables are on page 130 in your book. Okay, and so we have centripetal acceleration, our period, and our angular velocity. Okay, but this also means that if our centripetal acceleration AC equals v squared over r, okay, our angular velocity, we're going to rewrite this right here. Our angular velocity our speed equals r omega. Okay, then we can take our v squared over r, but we know that v equals r omega, so this is going to become r squared omega squared. If we substitute the velocity here with the rw, this becomes r squared omega squared, and we're dividing by r, this becomes omega squared r as our angular version of centripetal acceleration. Okay, so all these variables will appear in your living equation sheet. Okay, but if we have a centripetal acceleration, that begs the question: anytime we have an acceleration, we have to have a force. And so here's our force that we learned from the last chapter, that if that gravity happens, gravity is the existence of two massive objects, and they are always attracted to each other. That's just what happens. Here we have the force of the sun on the earth, and here we have the force of the earth on the sun. And these two are going to be opposite but equal to each other, regardless of the mass and regardless of the masses of the objects. These forces are equal to each other. They will just accelerate each other differently. So those of you that missed that question on the quiz, we need to learn that. Okay, that FSE is equal to negative FES. Okay, and really everything that entails is true, that these two are equal values. They just have different directions, and they act on the other object. Okay, and so these forces are given by the mass of your object, right? So the force acting here on Earth, so the force ES equals the mass of the Earth. Mind you, this is the Earth-Sun system. The mass of the Earth times the acceleration, keeping it traveling in a circle. All right, so that's going to equal m v squared over r, or m omega squared times r. These two are equivalent statements, and this is how you calculate the force acting on the Earth. But we also know that this equals force due to gravity, g, mass of the sun, mass of the Earth, over r squared, right? So this is centripetal acceleration. I'm sorry, the centripetal force, and this is our gravitational force. The centripetal force, the thing that is pulling the Earth, the thing that is keeping the Earth traveling in a circle, is the gravitational force. And so that's how we can set these equal to each other. So, okay, or it is also this mv squared over r. Okay, instead of this one, these are equivalent statements. So, if we want to find our orbital velocity of any object, okay, we need to solve this equation for v. How fast do we need to move in an orbit, or how fast is an object traveling in an orbit at a particular distance? So we're going to do that. So we have m v squared over r equals g, and sorry, this is mass of the sun, mass of the Earth. This is going to be mass of the Earth because we're just worried about the force on the Earth, divided by r squared. All right, and we want to get v squared by itself, so we're going to multiply both sides by r over me. Okay, so that's going to cancel some things. It's going to cancel our mass of the Earth. That's going to cancel one of our radii, and that's going to leave us with v squared. So v squared is going to equal g times the mass of the sun over r, which is the radius. And so we would square root that. And we wind up with the velocity of any object, because our mass of the Earth disappeared, so it doesn't matter what the object is. It could be a satellite traveling around the sun. It could be another planet. Is equal to g times the mass of the sun over r, and this whole thing square rooted, or to the 1/2 power. Now, this mass of the sun, it could also be the mass of the Earth if we're talking about the moon traveling around the Earth, or it could be the mass of the moon if we're talking about a satellite traveling around the moon. This is the thing that is pulling on the object, and this is the velocity you have to travel to go at this radius. And that's where we're going to stop for today. And it's time to get to work.